Hi everyone, in this video we are going to see how to find the equation of the circumcircle of a triangle whose three sides equations have been provided. Let's suppose you have a triangle like this and the equations of the three sides are like this. From these three equations we have to somehow come up with the equation of the circumcircle. Now how is the circumcircle going to look like? Well, the circumcircle is going to look something like this. To find the equation of the circumcircle from the given equation of the three sides of a triangle, there are actually 4 different methods we can try. So first we are going to look at method number 1. Let's suppose the vertices are P, Q and R, and let's suppose their coordinates are x sub 1, y sub 1, that's for P, and then x sub 2, y sub 2, that's for Q, and x sub 3, y sub 3, that's for R. Now how can we find the coordinates of P, Q and R? Well, we can simply solve the 3 given equations, and by solving each pair, we can find out the coordinates of P, Q and R. So I have noted it right here that solving equations 1 and 3, we can find x sub 1 and y sub 1. Similarly, solving equations 1 and 2, we can find x sub 2 and y sub 2. And also solving equations 2 and 3, we can find x sub 3 and y sub 3. We can use any method of solving simultaneous linear equations. Now we have coordinates of 3 points that lie on this circle, right? P, Q and R. Now what is the general equation of a circle? The general equation of a circle is kind of like this. Now if you look at the general equation of a circle, there are essentially 3 unknowns. What are the unknowns? Well, unknowns are G, F and C. So somehow if we can come up with 3 linear equations with these 3 unknowns, then we should be able to solve for those 3 unknowns. Now how can we form 3 equations? Well, we have the coordinates of the 3 points which are lying on this circle. So using the coordinates of each of the points, we can come up with an equation. So let's try to use the coordinates of point P and let's try to come up with the new equation. The new equation going to look like this. I have named it as equation number 4, and here you see everything is pretty much known except G, F and C. So this is a linear equation in G, F and C. Similarly, let's use the coordinates of the point Q and come up with another equation. This equation number 5 is again another linear equation, and the only unknowns are G, F and C. And exactly in the same way, using the coordinates of R, we can come up with the third new equation, and I have named it as equation number 6. Here again, the only unknowns are G, F and C. So on the 3 unknowns, we have 3 equations, and because we have 3 equations and 3 unknowns, we should be able to solve them and come up with the values of G, F and C. And once we have been able to find out the values of G, F and C, we can simply plug in the values in the original general equation that we took, and that will give us the actual equation of this circumcircle. I hope everything made sense in method 1. Next, we are going to take a look at method number 2. In method number 2, I am going to do a little bit of construction here. I am going to draw the perpendicular bisector for each of the sides, and the point of intersection of the perpendicular bisectors will give us the center of this circumcircle. I mean, it will give us the circumcenter. So I have drawn 3 perpendicular bisectors for the 3 sides, and let's assume that they intersect at the point O, which is the circumcenter. And also let's assume that the coordinates of O are h, k. So here, if we can somehow find out the values of h and k, and also if we can somehow calculate the circumradius, then we should be able to come up with the equation of the circumcircle. Now how can we find the values of h and k? Well, if we connect O with the 3 vertices, then you can see that OP will be equal to OQ will be equal to OR, and each of them will be equal to the radius of this circumcircle. And from here, we can create a couple of equations to find the values of h and k. First, let's try to find out what is the value of OP. Well, OP can be written like this: square root of h minus x sub 1 squared plus k minus y sub 1 squared. And similarly, OQ will be like this and OR will be like this. And then let's create the first equation, OP equals OQ. And then if we square both sides, we can say OP squared equals OQ squared. And from there, we can write it like this. And then we can write it like this. And here you see we have some equal quantities on both sides of the equal sign, so they will cancel out each other, and we are going to be left with something like this. And then I'm going to bring everything to the left hand side. Then our equation can be written like this. And if you carefully look at this equation, you will realize that this is nothing but a linear equation in h and k, because all other quantities are known quantities. We have already figured out the values of x sub 1, x sub 2, y sub 1 and y sub 2. So the only unknowns here are h and k, and this is a linear equation in h and k. And let's call it equation number 4 here. And similarly, we can create another equation. Let's take OP equals OR, and we can say OP squared equals OR squared. And from there, we can write it like this, and then we are going to expand it. So our equation will look like this. And here again, you see we have some equal quantities on both sides of the equal sign. They will cancel out each other. So our equation is going to look like this. And next, I am going to bring everything to the left hand side. Then our equation would look like this. And here again, you see we have yet another linear equation in h and k, because x sub 1, x sub 3, y sub 1 and y sub 3, they are all known quantities. So the only unknowns here are h and k. So this equation number 5 is the second new equation that we have been able to create. So now we have two equations in h and k. I mean, we have two linear equations in h and k, and we should be able to solve them and find the values of h and k. And now that we know the values of h and k, and also we know the coordinates of the vertices, we should be able to calculate the circumradius, and that circumradius is equal to OP or OQ or OR. So let's calculate the circumradius here, and that will be like this: square root of x sub 1 minus h whole squared plus y sub 1 minus k whole squared. This is the distance formula to calculate the length of OP. So now we know the coordinates of the circumcenter, and also we know the radius of the circle, meaning we know the circumradius, and then we should be able to find out the equation of the circumcircle. That's pretty easy. We can use the standard formula, and the standard formula going to look like this: x minus h whole squared plus y minus k whole squared is equal to r squared. That is the standard form of the equation of a circle. Here we know the values of h and k and r, of course. So this is the equation of the circumcircle. I hope all the steps made sense here. This is one of the ways to find the coordinates of the circumcenter. In the next method, I am going to show you another way of finding the coordinates of the circumcenter, and let's go to method number 3 now. In method number 3, let's assume that the midpoint of PQ is D and the midpoint of QR is E. So what would be the coordinates of D? Well, the coordinates of D, if we assume to be x sub 4, y sub 4, then their values would be like this, because D is the midpoint of PQ. We know the coordinates of P and coordinates of Q. So we can easily find out the values of x sub 4 and y sub 4 using the midpoint formula. And similarly, what would be the coordinates of E? Well, each coordinates can be written like this. If we assume them to be x sub 5, y sub 5, their values would be like this using the midpoint formula. Now let's try to find out the slope of PQ. So slope of PQ will be negative a sub 1 over b sub 1 from the given equation of PQ. So then what would be the slope of OD? Well, OD is perpendicular to PQ. So OD's slope would be negative 1 over the slope of PQ. So it will be b sub 1 over a sub 1, and let's call that m sub 1. Now if you think about the line OD, we know its slope and also we know the coordinates of point D. So using the point slope form of the equation of a straight line, we can say that the equation of OD will be something like this. And similarly, we are going to find the equation of OE. And for that, let's first try to find out what is the slope of QR. Well, slope of QR will be negative a sub 2 over b sub 2. So what would be the slope of OE? Well, OE is perpendicular to QR. So OE's slope would be negative 1 over the slope of QR, and that will be b sub 2 over a sub 2. And let's call it m sub 2. So now we know the slope of OE and also we know the coordinates of the point E. So using the point slope form of equation of a straight line, we can say that the equation of OE is going to be something like this. Now what is the point of intersection of OE and OD? Well, that is the point O. So solving the two linear equations, we should be able to find the coordinates of the point of intersection, which is nothing but O, and the coordinates would be h, k. So by solving these two equations, the value of x will actually be the value of h, and the value of y will actually be the value of k, and that way we can find the coordinates of the circumcenter. Once we know the coordinates of the circumcenter, then rest of the steps are exactly same as method number 2. The circumradius would be like this, and now we know the values of h and k, and also we know the value of r. So the standard form of equation of the circumcircle would be like this: x minus h whole squared plus y minus k whole squared is equal to r squared. So this method is also pretty much similar to the previous method, I mean method number 2. However, it's just a different technique of finding the coordinates of the circumcenter. Now once we are able to find the coordinates of circumcenter, then rest of the stuff is pretty easy. We just have to calculate the value of circumradius and then use it in the standard equation of circle. I hope everything made sense so far. Next, we are going to look at the final method, which is method number 4. In method number 4, we are going to use a completely different technique. Now let's think about it. We have been given the equations of the three sides. That means we have been given three linear equations, and from here we have to somehow form the equation of a circle. We know that the equation of a circle is a second degree equation, but the linear equations that we have been given, they are first degree equations. So using these three first degree equations, how can we come up with a second degree equation? Well, if we multiply any two of them, then that will give us a second degree equation. However, we have to impose the criteria of it being the equation of a circle, and the criteria would be coefficient of x squared will be equal to the coefficient of y squared, and the coefficient of xy should be 0. Those are the two criteria for a second degree equation to represent a circle. So here, if we multiply any two of them, let's see what happens. I'm just multiplying the first and the second equation. So our new equation will look like this, and now I'm going to expand it. So it is going to look like this, and then I'm going to reorganize the terms a little bit. So our equation would look like this. Now this equation is a second degree equation in x and y. However, we have to impose the requirements of a second degree equation to be the equation of a circle, and the requirements are like this. The coefficient of x squared should be equal to the coefficient of y squared, and the coefficient of xy should be 0. So once we impose these requirements, then this equation will actually represent a circle. And guess what? In this equation, we have used all the parameters from the first two linear equations. So this equation is actually missing out some parameters from the third equation, from the third linear equation, right? So somehow we have to come up with such an equation where we will be using all the parameters from the three given linear equations. And for that, what can we do? Well, we can actually form different pairs of products. For example, we can say L sub 1 times L sub 2, that will be one equation, and then L sub 2 times L sub 3, that would be another equation, and then L sub 1 times L sub 3, that would be another equation. And then if we combine them somehow, if we take a linear combination, if we simply add them up, that will also present the equation of a circle. And of course, ultimately we are going to impose the requirements for it to be the equation of a circle. But if we simply create three pairs of products, their sum will definitely represent a circle, and in that sum we will have all the parameters from the three given linear equations will be used. So let's give that a try. So I'm thinking we could have a sum like this, where the first product will represent a second degree equation, the second product will also represent another second degree equation, and the third product will also represent another second degree equation. And if we add them up, we are ultimately going to get another second degree equation, and on that we are going to impose the requirements for it to become the equation of a circle. And also we need to somehow prove that yes, this equation in fact satisfies the coordinates of P, the coordinates of Q, and the coordinates of R. So let's try it out. If we use the coordinates of P in this equation, the value of L sub 1 will be equal to 0 because P lies on L sub 1, P lies on that straight line, and similarly L sub 3 will also be equal to 0 because P also lies on the third line, which is L sub 3 equals 0. So if we use the coordinates of P, then L sub 1 will become 0 and L sub 3 will become 0. And now if you look at this combined equation, the first term becomes 0 and the second term also becomes 0 and the third term also becomes 0. That means ultimately the left hand side of this equation evaluates to 0. That means P's coordinates satisfy this equation. That means this equation stands valid with the coordinates of P. And similarly, let's try the coordinates of Q. For coordinates of Q, L sub 1 will become 0 because Q lies on the first straight line, and similarly L sub 2 will also become 0 because Q also lies on the second straight line. So from here again, let's evaluate the left hand side of our new equation, and as you can see, the left hand side also evaluates to 0. So when we use the coordinates of Q, the new equation that we created, it actually stands valid. Alright, let's try the coordinates of R. For coordinates of R, as you can see, R actually lies on the second straight line and the third straight line. So L sub 2 will be equal to 0 and L sub 3 will be equal to 0 when we use the coordinates of R. And from here again, let's try to evaluate the left hand side of the new equation, and as you can see, the left hand side actually evaluates to 0. All the three terms become 0 eventually. So when we use the coordinates of R, we can see that the equation still stands valid. That means this is such a second degree equation which is satisfied satisfied by the coordinates of P, coordinates of Q and coordinates of R. That means this equation would become the equation of our circle. However, we have to impose the requirements for it to become the equation of a circle. And because we are taking a linear combination of these three products and we are going to impose the requirements for it to become the equation of a circle, I am going to take this kind of a linear combination. I am going to use k sub 1 times the second product and k sub 2 times the third product. And of course k sub 1 and k sub 2, they are just real numbers. And then on this equation, if we impose the requirements for it to become a circle's equation, then we are going to get two equations from here, and those two equations will be in k sub 1 and k sub 2, and from the two equations we should be able to solve for the values of k sub 1 and k sub 2, and once we know the k sub 1 and k sub 2 values, then we should be able to plug in there and come up with the equation of the circle. If we do not use the k sub 1 and k sub 2, that linear combination may not satisfy the requirements of the circle. So we have to take such a linear combination of the three products so that it satisfies the requirements for the equation of a circle. So once we impose the requirements, once we find the proper values of k sub 1 and k sub 2, then it's just a matter of plugging in the values of L sub 1, L sub 2, k sub 1, L sub 3, k sub 2, and then find the equation that will give us the equation of our circumcircle. I hope all the steps of method 4 made sense. This brings us to the end of this video. Thank you for watching. See you in the next video.